Now, really quick before we start, note that if you have something like, let's say x times sine of x, do note that this can be rewritten as sine of x over 1 over x, right? Because you can put this in the bottom to turn it into a fraction. Well, watch, how about something like this? X squared times the natural log of 3 minus x. So this does not look like a fraction, but you could rewrite this as follows. You see what I'm saying? This is a trick that we should get used to. Turning something that's not a fraction into something that is a fraction by reciprocating one of the pieces underneath the other. Another thing, 1 divided by infinity, let's call that 0. 1 divided by negative infinity, let's call that 0. Similarly, 1 divided by 0, let's call that infinity, and negative 1 divided by 0, let's call that negative infinity. So let's get used to these things and let's try some problems. So let's try these problems here, starting with number 7. So we have this here, and I think I remember what I saw you write. You did that one trick where you can reciprocate one of the pieces so that we have a fraction, basically. I think that's what I saw you do. ln of 0 is technically negative infinity, but then with that negative, it makes it positive infinity. 0 here, 1 divided by 0 is, we'll call it infinity, right? 1 over 0, we'll call it infinity. And so infinity over infinity is one of those indeterminate forms. I had them written down here from another video. These are all the indeterminate forms. Whenever you have something like this, you can use L'Hopital's rule. So we have that here now. So let's hit this with L'Hopital's. So equals limit x approaches 0 from the right. Negative is just negative. The derivative of the numerator is 1 over x. The derivative of the denominator is negative 1 over x squared. If you clean that up, we have limit as x approaches 0 from the right. Clean up that mess, it should just be x actually. And so if you plug in 0 from the right into that, it would just be 0. Now here, I think I did this problem in a different video, but I did it using a table of values. Let me do it a different way here. So if you plug in 0, it's basically going to be 0 over 0. And I think I saw you do that. So let's hit this with L'Hopital's rule. And I think I saw you do that as well. And you got this here. And if you plug in 0 again, it's 0 over 0. Because e to the 0 is 1. 1 minus 1 is 0 over 0. So do L'Hopital's yet again. But I think this time is when we have to remember that the derivative of e to the x stays e to the x. If you plug in 0 here, you get e to the 0 over 6 times 0. E to the 0 is 1 over 0. And that trends toward infinity. So I think the key part was to remember that the derivative of e to the x is e to the x. And this should be infinity. How about this one here? Now, here's what I'll remind you of. For a trig function, cosine of, I don't care what you put in there, whether it's a big number or a small number. Remember that cosine is bounded by 1 and negative 1. So essentially, regardless of what you put in here, the input, the output is going to be bounded by negative 1 and 1. And you can see that graphically because the graph of cosine looks something like this and just keeps going, where the upper limit is 1 and the lower limit is negative 1. So what I'm saying is this: if x becomes a huge number, in the numerator, it's going to get cosigned. So it's going to shrink it to a number between 1 and negative 1 for the numerator. So the numerator is really small. It's between negative 1 and 1. But the denominator has no function like cosine acting upon it. If you plug in a huge number here, it's going to be huge. So you essentially have a small number over a huge number, which trends toward 0. And then for 45, your work was pretty much correct. There's really no need for me to go over this one because what you did was right, but I'll just run through it nonetheless. So you rewrote the original problem like that to make it look like a fraction. If you plug in infinity, it would be 0, it would be 0 over 0. So 0 over 0 is indeterminate form, so we can hit this with L'Hopital's. That'd be limit as x approaches infinity of cosine of 1 over x times negative 1 over x squared over negative 1 over x squared. These are gone. Plug in infinity here. 1 over infinity is 0. Cosine of 0 equals 1. I believe you got that answer, so I don't have to really elaborate upon this. Now, number 53. Anytime you have variable to the power of a variable, we are prepared to use a natural log. This is a number. The whole thing is a number. I'm going to call that number y. And I'll write this again as y equals limit as x approaches 0 from the right, 3x to the x halves. So I remind you that the goal is to solve for y because y equals the original expression. Solve for y. Okay, now I have an equation. If I feel like it, and I do feel like it, I can take the natural log of both sides. And this natural log can essentially invade the limit expression. So I have limit as x approaches 0 from the right, natural log of this here, and then recall your log properties from earlier math classes. How that if you have things being multiplied, you can expand it by addition. So this is natural log of 3 plus natural log of x to the x halves. Keep this in parentheses. And now we can split up using limit laws, limit of this plus limit of that. And we have limit as x approaches 0 from the right, ln 3, plus the limit as x approaches 0 from the right of x to the x halves. Now, a couple of things. This expression does not depend on x's, so I could dismiss the limit symbol because there's no x's here. So this is just ln of 3 plus, and then recall for logs, this should have an ln right there. Recall for logs that if you have a power on your argument, that power can go to the front as a coefficient. So we have limit as x approaches 0 from the right of x over 2 times ln of x, and that can be rewritten. So we have natural log of 3 plus limit x approaches 0 from the right. We can write this as natural log of x over 2 over x. That's sort of the trick that we've been using for a while. And now if you plugged in 0, it would be like an infinity over an infinity or like a negative infinity. It's going to be infinity over infinity. So we can hit this with L'Hopital's. So we have natural log of 3 plus carry your limit. And the derivative of the numerator is just 1 over x. The derivative of that would be negative 2 over x squared. Let's take this up here. So this is ln of 3 plus the limit as x approaches 0 from the right. If you clean that up, it's going to be negative x over 2. And x is approaching 0. So 0 over 2 is just 0. So all you're left with is ln of 3. And what did this equal? That equaled ln of y. So I have ln of y equals ln of 3. And so y equals 3. And so the whole answer is just 3. Because y was the goal, because you let it equal the original problem. So the original problem equals 3. And what you could always do for all of these problems, if you were to go to Desmos, and if you were to type in just this here, you would get a picture. And you'd notice that in that picture, as your x's approached 0 from the right, you would notice that the y coordinates are getting awfully close to 3. So just to recap, the reason that we use the natural log for a problem like this was for this step right here. You see how from here to here, the exponent became a coefficient, And that's good because it's now no longer it's no longer a variable to the power of a variable. Now they are side by side because we could move this to the front because there was a natural log. So that's the convenience of calling upon a natural log. It allows a variable exponent to become a variable coefficient, which can then be flipped to become like a fraction, so we can use L'Hopital's.